Today we are going to take a look at the Shapley Shubik Power Index. Shapley and Shubik are two modern American mathematicians and economists. Shapley is a professor at UCLA of math and econ, and Shubik is a professor at Yale. They developed this system in the 1950s as another way of calculating the power of voting coalitions. Sometimes it gives you the same results as the Bonshoff Power Index, sometimes it does not. So, key things about the Shapley-Shubik Power Index. In this situation, we are going to look at sequential coalitions. Coalitions are formed in order instead of the coalitions being formed all at once. The players will join the coalition and cast their votes in an orderly sequence, so there is a first player, second player, third player, etc. In this method, we are concerned with the pivotal player, who is the player that contributes the vote that turns a losing coalition into a winning coalition. So, for this method, the player's power is obtained by counting the number of times that a given player is a pivotal player and dividing by the total number of times that all players are pivotal. This is basically the same thing that we did with Bonshoff, but we're using pivotal players instead of critical players and sequential coalitions instead of ordinary coalitions. So here are the steps. You want to list out all of the sequential coalitions, determine the pivotal player, count the number of times that each player is pivotal, and then divide the number of times the player 1 is pivotal by the number of sequential coalitions, and that will give you the Shapley-Shubik Power Index for player 1. You continue doing this for all of the players. So, here we have the weighted voting system. The quota is 4, and player 1 has 3 votes, player 2 has 2 votes, and player 3 has 1 vote. When we write out sequential coalitions, we are taking our 3 players and writing all of the different orders that they could vote in. So this is the number of permutations for 3 players. So one possible order is P1, P2, P3. And instead of using curly brackets, we are going to use essentially what looks like a greater than and a less than symbol. This denotes sequential coalitions. And you go through and you write out all of the orders for these 3 players. And continue. Once you have all of the sequential coalitions listed, now I'm going to go through and write out all of the weights for these coalitions. So in my first coalition, player 1 has 3 votes, player 2 has 2 votes, and player 3 has 1 vote. And I want to look and see where this coalition changes from a losing coalition to a winning coalition. Remember, our quota is 4, so we need 4 votes to win. So if I start here, after player 1 votes, I only have 3 votes. That is not enough to win. When player 2 votes, I now have 5 votes, which is enough to win. So player 2 was the one who flipped it from a losing coalition to a winning coalition, and player 2 is our pivotal player. So let's continue for the rest of the coalitions. I've written out all of the weights in order corresponding to the sequence that I wrote in the first column. So now let's go through and find the pivotal players. I start with 3 votes. After the next player votes, I have 4 votes, which is how many we need to pass our motion. So player 3, who cast that 1 vote, is our pivotal player. In row 3, we start after the first person votes. We have 2 votes. When the second person votes, we now have 5 votes, which is enough to win. So player 1 is our pivotal player. In the fourth row, we start with 2 votes after player 2 votes. Then player 3 votes, and we're up to 3 votes, which is still not enough to win. But after player 1 votes, now we have enough votes to win, so player 1 is once again our pivotal player. Next, after the first person in this coalition votes, we have 1 vote. The second person votes, we now have 4 votes, which is enough to win. So player 1 is our pivotal player. Lastly, after player 3 votes, we have 1 vote. When player 2 votes, we're now up to 3 votes. We don't have 4 votes until player 1 votes. So now we're going to go through and count. Player 1 is the pivotal player 4 times. Player 2 is the pivotal player once. Player 3 is the pivotal player once, for a total of 6 coalitions. For this method, we are going to use the notation sigma sub 1, sigma sub 2, sigma sub 3 to represent the Shapley Shubik power distribution. So player 1 is the pivotal player 4 out of 6 times, which is 2/3. Player 2 is the pivotal player 1 out of 6 times, and player 3 is the pivotal player 1 out of 6 times. So this right here is the Shapley Shubik power distribution. Because it lists out the power of all of the players. Now, if you go back to your notes from last class, we had this same setup where the quota is 4 and the power of the players are 3, 2, 1 in the last notes. When we calculated the Banzhaf power distribution for this same scenario, we had 3/5, 1/5, and 1/5. So the distributions are similar in that player 1 has the most power, player 2 and 3 have equal amounts of power, but the fractions are not identical. This method, the Shapley-Shubik power distribution or power index, has been applied to some large-scale voting bodies such as Congress or the UN Security Council. Those get a little more complicated because there are so many players. It's basically impossible to list out all of the millions, billions of sequential coalitions. So you have to get a little bit fancy with your counting methods, maybe use some computers, some combinations and permutations, and that kind of stuff that we have learned previously to make it more efficient. So let's pause and review some math. The multiplication rule, or the fundamental counting principle, says if there are m different ways to do x and n different ways to do y, then x and y together can be done in m times n different ways. So, an ice cream shop offers 3 different choices of cones in 5 different flavors of ice cream. Using the multiplication rule, how many different choices are there? assuming that you have one choice for cone and one choice for flavor of ice cream. You just do 3 times 5, which is 15. Another ice cream shop has 6 choices for cones, 32 different flavors of ice cream, and 9 different toppings. If you are only allowed to choose one cone, one scoop of ice cream, and one topping, how many orders are possible? You have 6 choices for cones, 32 choices for ice cream, and 9 choices for toppings, which is 1728 different orders. We did this first semester when we were looking at combinations and permutations in that unit. So, going back to voting, how do we count the number of sequential coalitions for 5 players? We can choose any of the 5 players to go first, so we have 5 choices. Then there are 4 players left. We can choose any of those 4 players to go next, then any 3 of the remaining players to go third. Then we have 2 choices left for the 4th spot, and there's only 1 choice left for the last spot. When we multiply that together, we get 120 possible sequential coalitions. So how many sequential coalitions would there be for 4 players? Well, you could do 4 times 3 times 2 times 1, which is the same as 4 factorial, which is 24. So, when you are trying to find the number of sequential coalitions for n players, all you do is n factorial. Now, factorials get large rather quickly. You can see that if there are 5 players, there would be 120 potential sequential coalitions. So, that's why this method is tricky to do by hand, because even having 5 players gets to be ridiculously tedious. Other than that, it's very similar to the Bonshoff Power Index, which we looked at last class. So go ahead, take your practice, and get to work.